Uh, Welcome to video 2 of chapter 7, 7.2, measuring the quality of a survey. You may be wondering why I was laughing. Well, I already recorded this lecture, but my Spotify was playing, so the entire thing, you can only hear my music playing in the background. So let's give this another try. Hopefully it'll be slightly better than my first one. I mean, maybe. So evaluating surveys, statisticians evaluate the method used for a survey, not the outcome of a single survey. So, for example, if a group of researchers were to survey 1,000 randomly selected people, we'd expect the results to vary from sample to sample, because we would want to know how the group did as a whole, and we evaluate the estimation methods, not the individual estimates. So the goal is to be accurate and precise. So an estimation method should be both accurate and precise. Accurate, the method measures what it is intended correctly, or correctly estimates the population parameter and aims in the right direction. Precise, if the method is repeated and the estimates are very consistent. There's a great couple of pictures of this in your book, and there's always that textbook one with the dartboard being accurate and precise versus precise not accurate, if you don't quite know what accurate and precise are. So in repeating the survey, we would arrive at nearly the same estimate. So accuracy and precision, which are bias and standard error. So bias goes with accuracy, while precision goes with standard error. Bias is a measure of the accuracy. So if only basketball players are measured to estimate the proportion of Americans who are taller than 6 feet, then there would be a huge bias for the larger, because the average height for NBA players, maybe that's not assumed here, but if you took a sample of NBA players, the average height's like 6'6". So basically everyone in the NBA is taller than 6 feet. So it would really be a really biased estimator for your proportion of Americans who are taller than 6 feet. Standard error, measure of precision. So if the sample size is only 3, the estimate of the proportion of tall people using the sample is more likely to be far from the proportion of tall people in the U.S. The variability among samples, the standard error, will be large. So simulation 1, we have a small population. So our population here will be a committee has 8 members: Abby, Beth, Kathy, Don, Ed, Frank, Gary, and Henry. 3 of those committee members are randomly chosen for a subcommittee, so we can think of that as a sample. So the population proportion of the number of females, well, we have 3, Abby, Beth, and Kathy. So our P is going to be 3/8, or 0.375. And there are 56 possible combinations of a sample of 3 people from this 8. So we're trying to figure out the sample proportion of the number of females for each possible random sample. So here's all of them, all 56 samples, and ABC, that means female. So A means female, B means female, C means female. So we can see that right here. 100% of the sample is female, so 3 out of 3. While this one would be 2 out of 3, 66.7. This would be 1/3, 1 out of 3, because A is the only one that would be female. And then this one, 0%, 0 out of 3 would be female. So in a population, the proportion who have a certain characteristic is called the population proportion. It's pretty that shouldn't be scary. The population proportion is denoted by just this regular P, no symbols. So on a simple random sample of n individuals, X is the number who have the characteristic that we're interested in. So the sample proportion is P hat, and that equals X over N, so the number that we're interested in over the total sample. So like on our previous example, our X here would be 1 and our N would be 3, because we have 1 female and 3 total. So no matter how many different samples we take, the value of P, the population proportion, that should make sense, always stays the same. But the value of P hat changes from sample to sample, and we can see that on the previous slide. It goes all over the place. It goes from 100, 2/3, 1/3 to 0. So if several samples are drawn from the population, they're likely to have different values for P hat. Since P hat varies, every time a sample is drawn, P hat is a random variable. And P hat is random because it depends on a random sample. And there's a statistic we use to estimate the population parameter regular P. And the first observation reminds us that statistics are based on random samples. Just forget this point. You can read through this. I don't think this. But we shouldn't know ahead of time with certainty exactly what estimates our survey will produce. So if several samples are drawn from a population, they are likely to have different values for P hat. The value of P hat varies each time a sample is drawn. P hat is a random variable and it has a probability distribution. So the probability distribution of P hat is called the sampling distribution of P hat. And we can think of this rectangle as a population, and each of these circles is a sample from it. So we could also have a sample like this, like this, like this, but these are just examples of samples. That rhymed. The probability distribution of P hat is called the sampling distribution of P hat, and from our example, we have 10 out of 56 where we had a subcommittee of 0 females, while we have 30 out of 56, you can see it right here. About 54% of the time we had a subcommittee with 1 out of the 3 subcommittee members to be a female. 27% where there's 2 of the 3 on the subcommittee were female, and then only 1 time out of the 56, which is about a 2% chance, where all the subcommittee members were female. So our sampling distribution, so the mu of sub P hat equals the regular P, and we can grab that from here, equals 0.375, or 37.5%. And the distribution of sample proportions has a mean, for this example, has a mean of 37.5. And so the mean of the collection of all sample proportions, so every single sample, if you were to calculate a mean off of that, which would be a weighted mean, it would be this 37.5. But in other situations, it doesn't have to be that, but it would be equal to the regular P. So to kind of explain this a little bit more, one population proportion, many sample proportions. Our estimator P hat is not always the same as our parameter. We saw that before. The mean of the sampling distribution is 37.5%, the same value of P. This indicates that the estimator P hat is unbiased. Our estimator has no bias because on average it is the same as the parameter value of P, and so we could call that unbiased and then accurate estimator because there's no bias. It's really close to the actual P, and bias is measured using the mean of the sampling or the center of the sampling distribution, and it's the distance between that mean, or it could be median, just depending on the sampling distribution, but typically the mean and the population value. And since our example had 0.375 in both cases, there was no bias. So the sampling distribution, talking about this more, sigma sub P hat equals the standard error. And we get this from the table right here. It's 23.9%. So the standard deviation of a sampling error, or of a sampling distribution, is called the standard error. And this one, we pulled it out from the table, is about 23.9%. So precision is measured using the standard error. And when the standard error is small, we say that the estimator is precise, the same as the parameter. But the sampling tells us how far away typically the estimator may stray from average. So precision is reflected in the spread of the same only 8 people. That made no sense. Just think of it as the standard deviation of the sampling distribution. So our first simulation, we had a good estimator, but our precision was bad because our p hat, or like our mean p hat, was 0.375. Our standard error was 2/3 of it, and that's really not good. So how can we improve that? And so we need to use another simulation to understand it. So let's just say we have a population of 8 people, and these 8 people are named 1 through 8. That'd be a really bad name. And so in this world, people are they only like cats or they only like dogs. So we have 2 cat people out of the 8, so we're taking samples of 4 people. What proportion of our sample will be cat people? So p hat isn't going to always be the same as regular p, which would be 0.25. And then this one, it could be 0, because we could take all dog people out of the 4. But it could also be 50%, where we take the first 4, or it could be these 2 and these 2. Or it could be 25%, where we take these 4, or we could take this one and these 3. There's different values. But the mean of the sampling distribution is 25%. And that's the same as p. But in the standard deviation, which is slightly better than the last one, because our sample size went up from 3 to 4, is 16%. So the standard deviation, or sampling distribution, we remember, is called the standard error. Let's use a larger population, so 1,000 people. 250 are cat people, which is 25% of the population. Let's just say we take a random sample of size 10 and find the sample proportion of cat people in the sample. And then using technology, we do 10,000 samples. And so these are the results on this slide. So our mean is about 0.25, and our standard deviation they give us is 13.56%. And that would be in a table somewhere. I don't know why they didn't give it to us. But since the center of the distribution is about 25%, we have an unbiased or accurate estimator of p hat, and our bias is 0. And even though the larger population and sample size were used, and the variation of p hat is less because our estimator is more precise, our standard error was smaller than right here. We just took a larger sample size. That's why it's smaller. And so in general, the population size is large relative to the sample size, so the precision has nothing to do with the size of the population, only with the size of the sample. And that's what I kind of alluded to like a few seconds ago. So the mean of all sample proportions in a sampling distribution will always be equal to p, the population proportion. And the standard error will be smaller for larger sample sizes. And the notation for the mean of sample proportions is this mu sub p hat. And the standard deviation is going to be this SE, or this sigma sub p hat. So for an SRS, the bias is 0. We talked about that. That means that the mean of all sample proportions in a sampling distribution subtracted from that p is going to be 0, which means it equals that p. And for an SRS, the precision is better for larger sample sizes, because you can look, this n as this n gets larger, this entire number inside the square root is getting smaller and smaller because it's being divided by more and more. And so, equivalent to this statement, the precision and bias are independent of the population size, as long as the population size is 10 times larger at least, and that's the optimal point for the standard error, because there's big, it gets kind of, so you would be doing something very bad statistics if you were taking a sample size larger than that 10, and you'd have to manipulate it mathematically, and it's not a good measure of the standard error. It's a mess. So, but don't worry about that. Just remember the sample size being at least 10 times larger. We talked about these formulas on the previous slide, but the mean is equal to p, and the sample size, if it's increased by a factor of, this might help you a little bit more. So if this n was 1, then it would be whatever that value is. But if we multiplied that n times 4 to make it 4, our standard error would be half the original standard error. So the following conditions, or if the following conditions are met, the sample is randomly selected, and the sampling is without replacement, which SRS is. The population needs to be much larger, which means 10 times larger. So our population in Pet World should be 1,000 people, not 100. 25%, that would be our P, our cat people. And we're planning a survey in which we take a random sample of 100 people without replacement. So, and we calculate the proportion of people in our sample to our cat people. What value should we expect for our sample proportion, and what's the standard error? Now, I know some of the answers are there, but pause this and think about it, and then answer. Alright, so our sample proportion is going to be unbiased, so it would be the same as the population proportion, 25%. And the standard error, this is wrong, it should all be under the square root, but I'm going to pull up my calculator. So we have 0.25 times 0.75, that's what 1 minus 0.25 equals, divided by 100, so 0.25 times 0.75, that equals 0.1875, and to divide it by 100, we would just move this decimal point over left 2 spaces. So then we get this entire number right here is 0.001875. To square root that, we'd get this number, so about 4.3%. And our sample size condition meets our criteria, because 100 times 10 is 1,000, so the population is at least 10 times larger. So 1,000 people is our population, 25%. Our conclusion from this is we interpret the values to mean that if we were to take a survey of 100 people from Pet World, we would expect about 25% of them to be cat people, give or take 4.3. And the give or take means that if you were to draw a sample of 100, I were to draw a sample of 100, our samples would typically differ from the expected 25% by about 4.3 percentage points. And we could think of this as like an interval. So 25 minus 4.3, that's 20.7. 25 plus 4.3 is 29.3. So our middle is right here. You could draw something from right here, but you wouldn't be past this 29.3. And I could draw something from over here, or it could be on 25%. But it'll never leave this interval. It'll always be between 20.7 and 29.3. So another example, 20 million Americans attend college each year, and 12 million of them, or 60%, borrow to cover the costs. If many random samples of 500 American college students were taken about the college debt, what would the mean and standard deviation of the sampling distribution be? So I recommend that you pause the video right now to figure these out using these formulas. Well, this one isn't really much of a formula, but you can figure that out. Alright, so our mean is going to be P, and that's 60%. And our standard deviation, our standard error, we plug in that P, 0.6 times 0.4, equal, and divided by 500, I forgot to say that, equals about 2.2%. I'm going to bring up the calculator really quickly. So 0.6 times 0.4, this part equals 0.24, divided by 500. This entire thing is equal to this, 0.0048. Now we need to square root that, and that's how we get this number, about 2.2%. So here's an example. Think of McDonald's when they have that Monopoly game. I recommend a really good documentary, a docu-series called McMillions. It's on HBO. It's free. Pretty good. I love it. Please watch it whenever you have time. But the customers peel off their tickets to see whether they won the prize, and the population proportion that win is 0.25, and we had 70 people come buy a soft drink between noon and 1. They're pretty busy that day, so we let P hat be the proportion that won a prize. So we need to find the mean and standard deviation for that. So pause the video, see if you can do it. But part of the answer is right here. So our mean is going to be P, which is 0.25, and our sample size is 70. And our standard deviation of this, plug it in. I'm going to put it in the calculator just for those that may not see all the steps right away. 0.25 times 0.75, and we did that earlier, it should be 0.1875, and divided by 70. So this entire thing equals 0.00267. Now we need to square root that, and we get this number, so we're good. The trouble with P, I might have addressed this a little bit earlier, we never know what this is. In order to get it, we would have to take every single sample from a population to figure it out. But it's just not possible. It'd be expensive. But the main application of sampling distributions is to address bias and precision of a sample. And so like I said, P is unknown, so we are trying to estimate that. So now this formula, it cannot be calculated because we don't know these P's. So we use P hat as an estimate for P, and this gives us a good estimate for the standard error. So P hat in for P, 1 minus P hat divided by N. So that does it for 7.2. Let me know if you have any questions or comments. So see you next time.